Hey guys, what's up and welcome back to the Rocket Shop. My name is Philip and today we're going to explore some alternative rocket designs and the reason why they even exist. For better accessibility, this video is divided in chapters. The timestamps of these chapters are on screen right now. After watching this video, you will know everything important about these alternative rocket designs. Picture a rocket launch in your head. What do you see? I can tell you. A cylindrical rocket, maybe side boosters or one of the space shuttles attached to it, racing toward the sky under the power of roaring engines. Now to the pad. A launch mount, flame trench beneath. Deluge systems spray water onto the pads to protect it. A launch support tower or strongback, cables attached to a rocket disconnecting as it lifts off. That is what a typical rocket launch looks like. But it doesn't have to. Apart from the traditional rocket designs we know, there are other options how to get stuff into orbit. These designs don't necessarily lift off from anywhere and only use rocket motors during later portions of the flight, differing drastically from what we know. Today, we are closer than ever to actually use some of these concepts to our advantage and try to reshape the way we see rockets. But why do they even exist? Is the currently preferred way of getting to orbit really worth replacing? And have these alternative options even got the needed capabilities to replace traditional rockets as we use them today? A lot of questions requiring a lot of answers. But first, we have to take a look at the different alternative rocket designs and how they work. When going to space, multi-stage rockets with a vertical takeoff from the ground are the way to go. They offer pretty good efficiency, high reliability, and require little supporting equipment on the pad. Such traditional rockets have served us for almost 70 years, and until now, they've done a good job. But in the 21st century, rocket science isn't all about physics and making a rocket anymore. A modern launch vehicle has to be as cheap and reliable as possible. But other than making a rocket reusable, there is a more interesting way to lower launch cost, and that has to do with our beloved rocket equation. Yes, we're talking about it again. In the year 1903, Russian physicist Konstantin Tsiolkovsky came up with the rocket equation, a physical equation that tells us how much delta V, or change in velocity, a rocket can achieve. Due to us normally building rockets around the delta V requirements and not the other way around, we can figure out how much propellant we are going to need to bring our payload to orbit and how much of the rocket's total weight is actually made up of propellant. But the more propellant we require, the more engines we have to add and the more inefficient our vehicle gets. Due to this reason, we introduce staging events to basically separate our rocket into multiple smaller rockets with less weight and less delta V requirement. But despite that, the first stage, which is only needed for the first few minutes of the flight, makes up more than 2/3 of our rocket. That's a lot of fuel just to get up into space. The remaining 3/4 of velocity needed to get into orbit, which is a lot more than just space, are all provided by the tiny second stage. All this extra propellant causes our rocket, and with it launch cost, to increase dramatically. Larger rockets require more infrastructure and higher manufacturing efforts. The cost of the fuel alone makes up for a significant increase. And if that wasn't enough, most first stages aren't reusable to make things even worse. Effectively, we are throwing valuable fuel and money away for just a tiny bit of delta V. That can be done better, right? In fact, it can. The first few kilometers per second of delta V don't have to be provided by rocket motors. By using external energy input, the amount of required fuel and structure of the vehicle can be reduced. If we can find a way to gain kinetic energy through our launch infrastructure, we can enhance the efficiency and ecological impact of our vehicle dramatically. So, to increase rocket performance, we need to replace as much of the rocket as possible with other impulse applying methods. And depending on what we use to get the externally applied impulse, we get different alternative rocket designs. So, what options do we have? The first alternative rocket design, and the only one to be successfully tested, is air launching. Air-launched rockets don't ignite their engines when in vertical position, but rather do so while lying horizontally. Instead of a proper launch pad, air-launched rockets are deployed by an aircraft. They are either dropped from the carrier or lift off from its back if the vehicle is a spaceplane. Through this, air-launched vehicles begin their journey to space with an initial velocity of about 200 meters per second. Their dropping altitude is located at about 10 kilometers or above, meaning the air resistance is way lower than on sea level. Additionally, the nozzle of the first stage engines can be better adapted for higher specific impulse in thin air, making these engines a tiny bit more efficient. The total impulse gained from the aircraft carrying the rockets certainly isn't that significant compared to the 7,800 meters per second of orbital velocity, but it still has an impact on the overall propellant need of the rocket. Although air launching doesn't do much in terms of replacing the first stage of a rocket, it has two advantages over all other alternative rocket designs. Firstly, air-launched rockets have the advantage of possessing a mobile launch pad. Traditional rockets are bound to launching from pre-designated pads and can only launch if the pad is ready and the weather in the area is good. An air-launched rocket can launch from practically anywhere and isn't bound to weather or an inclination range dictated by a launch site, making delays less likely. And the second advantage is availability. Air launching isn't much harder than ground-based takeoff and requires little additional infrastructure other than a large enough aircraft. Of all alternative rocket designs, air launching is the only one to ever enter service or even be properly tested in multiple attempts. But on the other hand, air launching also has some slight disadvantages. Since the reduction in delta V requirement isn't that high, only 200 meters per second, it seems kind of unnecessary. The work that has to be accomplished to achieve reliable air launch capabilities is just not always worth the time and money for such a small increase in efficiency. The only real advantage air launching offers is the mobile launch pad flexibility. Additionally, the size and therefore the payload mass of an air-launched vehicle is limited by the maximum takeoff weight of the aircraft it's launched from. Thankfully, we have large enough aircraft that allow the launch of rockets with a somewhat reasonable payload capacity. But even these are still quite small and don't exceed a payload mass limitation of just a few tons. Every attempt to air-launch greater payloads leads to the required development of ridiculously large aircraft like the Stratolaunch ROC or the once fantasized double fuselage Antonov 225. And we don't even want to talk about the operating costs of such aircraft. Due to these constraints, air-launching rockets is somewhat unnecessary, and just going the traditional way isn't even that much worse. But despite that, there actually were some air-launched vehicles developed and operated over the years. Among them are Virgin Orbit's Launcher 1, a small-set launch vehicle which is dropped from Boeing 747, the Pegasus launch vehicle developed by Orbital Sciences and Northrop Grumman, and the crewed suborbital spaceplanes of Virgin Galactic with their specially designed White Knight II carrier aircraft. But these vehicles profit mostly from having a mobile launch pad and not from the delta V requirement reduction. second alternative we're going to talk about is spin launching. Other than air launching, this has never been done before. The idea behind spin launching isn't just giving your rocket a slight boost, but to replace the first stage entirely. Therefore, a rocket using this method would only be made up of a single stage and require only small amounts of fuel. But since the first stage is missing on such a design, the near delta V the first stage normally offers has to come from somewhere else. And that is where the spinning comes in. Spinning, as in spin launching, doesn't refer to the rocket rotating, but to a giant centrifuge that is used as a mass accelerator. In this large centrifuge, a long arm would slowly accelerate the rocket mounted on its tip to multiple thousand rotations per minute. To reduce air resistance and the resulting heating, the entire centrifuge is in a vacuum. Once the rocket reaches a velocity high enough to reach orbit with the additional second stage, which should be between 6,000 and 8,000 kilometers an hour, the centrifuge arm releases the rocket and fires it into a channel tangential to the centrifuge. As the rocket smashes through a thin membrane that isolates the vacuum from the outside, the centrifuge is flooded with air. Since the exit velocity of the rocket is high enough to get all the way into space, the second stage only lights its engine once the vehicle is already in space and moving at multiple kilometers per second, requiring less delta V to achieve a stable orbit than a typical ground-launched traditional rocket design. So basically, we're just yeeting a rocket straight up into space by spinning it around. The advantages this type of system brings are quite simple. Since rocket launch from the centrifuge only requires a second stage, propellant and manufacturing costs are greatly reduced, but the payload stays the same. Additionally, the vehicle can be of simple design and utilize pressure-fed engines for in-space propulsion, as well as these engines being optimized for in-space operation. Furthermore, the centrifuge system can easily be restocked with new launch vehicles and conduct multiple launches per day without major maintenance, since it isn't tortured by exhaust gases like the typical launch pad. The centrifuge can also be erected basically anywhere, since they don't need large exclusion zones like typical launch pads due to the far lower noise emissions of a spin launch system and lower risk of large explosions since there is less fuel involved. In total, spin launching offers some major advantages over traditional ground-launched rockets, at least on paper. But in reality, there are some challenges that may render it infeasible. The main problem here are the physical forces on an object that is accelerated by spinning it around in the centrifuge. The rocket in the centrifuge gains velocity by spinning faster, hence the forward velocity of the vehicle increases. But at the same time, the rocket is pulled outward by centrifugal forces, which inflict high g-forces onto the rocket. And when the centrifuge rotates multiple times a second, trying to accelerate rockets to 8,000 kilometers an hour, these g-forces can be as high as 10,000 g's. And no, that is not a typo. Not only does the rocket have to withstand these forces, but the payload has to be reinforced as well, making satellites extremely heavy. And even if we can develop a vehicle strong enough to withstand the forces in a spin launch system, we got another problem. To enable precise orbital insertion, the rocket has to leave the centrifuge at a certain angle. And when rotating at more than 1,000 times per minute, releasing the vehicle just in the right moment is quite a challenge. The angle we need to achieve only has a tiny margin of error. Anything outside this small slot leads to mission failure. Getting the precision high enough to grant a correct orbital insertion is not impossible, but challenging at least. Despite the challenge, there is one company planning to offer rocket launches out of a centrifuge. Fittingly, this company is just named Spin Launch. Their design incorporates a centrifuge with a 100-meter diameter lying on its side. The rocket is accelerated to a speed of up to 5,000 miles or 8,000 kilometers an hour and gets thrown out of the centrifuge at a 30 to 45 degree angle relative to the ground. Using this setup, Spin Launch hopes to decrease launch costs to less than $500,000 per flight. They have already conducted multiple test launches using a 1/3 scale demonstrator, shooting a test vehicle on a suborbital trajectory. Despite being successful, these tests also showed the problems of the spin launch strategy. In the eyes of many, including myself, spin launching rockets already sounds quite crazy. But in fact, there may be an even crazier method of getting stuff into orbit without using rockets. As crazy as the idea appears, utilizing a literal cannon to shoot objects into space is actually a viable option. Just like the centrifuge of a spin-launched rocket, a space gun can induct the kinetic energy needed to get the rocket into space before it lights its own engines to get to orbital velocity. But other than a centrifuge, a space cannon may actually be able to shoot payloads into orbit directly without having to use rocket propulsion at all. We just need the exit velocity of our projectile to be high enough so it reaches orbital velocity after being slowed down by air resistance and gravity. In a space cannon, the payload is placed inside a shell protecting the satellite, which is then fired through a long barrel towards the sky. Since explosive would damage the shell, the projectile in a space cannon is accelerated by rocket motors either on the projectile or at the sides of the barrel itself. But space cannons also have a lot of practical problems. Accelerating a vehicle to velocities of about 10 kilometers per second in the barrel of a gun means extreme g-forces on our vehicle as it gets shot through the cannon. These may be lower than the insane 10,000 Gs in a centrifuge, but still in the 4-digit regime. Upon leaving the barrel, the projectile hits the surrounding air at hypersonic speeds. That leads not only to immense heating generated by the friction between the air and the skin of the projectile, but also to immense aerodynamic drag forces threatening to tear the vehicle apart. Additionally, achieving a stable orbit just by shooting an object into space is next to impossible. Therefore, we can't just put a satellite directly into space, but have to attach at least a few reaction control thrusters to our payload to make it stay in space. Furthermore, we may need an actual rocket as well, since the precision of a projectile fired from a large gun may not be high enough to properly reach the desired orbit. And the construction of such a gun is complicated as well. A space gun capable of shooting payloads into low Earth orbits has to be enormous. The required barrel length is linked to the launch acceleration and therefore has to be more than 100 meters in length. That's why such a space gun is also very complicated to move around and basically limits it to one inclination. Despite all the craziness and the complications, the idea of building a space cannon is actually quite common. Over the last century, there were dozens of attempts to build one, but no objects have been shot into orbit until today. The first thing that got somewhat close to a space gun was the German V3 cannon, one of the Nazis' vengeance weapons. This gun was pretty much a shrink down and weaponized version of a space gun used to shoot projectiles at London from European coastlines. The farthest the space cannon project ever got was the HARP project, set up by the Canadian and American Department of Defense in the 60s. HARP stands for High Altitude Research Project and collected data about the higher levels of our atmosphere and re-entry profiles. But other than weather balloons or rocket, HARP used a 16-inch caliber space gun to fire its projectiles on suborbital trajectories up to 180 kilometers. The exit velocity of the projectiles was about 2,100 meters per second, only 1/5 of what's needed for orbit, and the maximum launch acceleration was, I'm not kidding, 15,000 Gs. Although there have been multiple other attempts made to build a working space gun, not a single object has been shot into orbit until today. Should there ever be a functional space gun somewhere in the future, it will, sadly, most likely be used as an anti-spacecraft weapon system. space gun and stretch the barrel to get our extreme accelerations down to normal levels? Well, we convert it into a mass driver. Basically, a space gun of multiple kilometers in length, mass drivers accelerate vehicles along a horizontal track. Upon reaching the end of this track, the vehicle either lifts off using wings or is directed upwards. Depending on the length of the track, the velocity the vehicle reaches upon leaving the track can be anywhere between being fast enough to get a second stage into space or even reaching escape velocity. On a technical level, these tracks would most likely not utilize the same principles as space guns. Instead of rocket motors mounted at the side of the barrel, which isn't feasible when using tracks of such lengths, mass drivers accelerate through electromagnetic fields, rocket sledges, or vacuum tubes, similar to the Hyperloop concept. The big advantage mass drivers have compared to space guns is the far more gentle acceleration. By stretching the tracks to even greater length, we may actually be able to bring the acceleration down to levels the human body could withstand. Therefore, we don't need to reinforce payloads to survive thousands upon thousands of Gs, and other than on a space cannon, crewed missions can actually be launched on a mass driver. Additionally, mass drivers can save quite a lot of energy. Since the vehicles take off horizontally instead of vertically, the lift generated by either the fuselage or additional wings can reduce the amount of energy needed to get the vehicle into space. Due to riding along a track instead of being violently fired through a gun barrel, the entire assembly experiences less wear than a space gun and requires less maintenance. But mass drivers also have some major disadvantages, many of them shared with space cannons. For example, the highly increased air resistance and heating caused by the immense friction generated by an object flying through the air at orbital velocity remain. The acceleration may be a lot lower, but payloads launched from a mass driver still need an aeroshell to get to orbit undamaged. And after all, the biggest advantage a mass driver offers is, at the same time, its biggest disadvantage. The track the sledge carrying the vehicle accelerates on requires a certain length. Depending on how low the acceleration forces should be and what the value of takeoff velocity is set to, the track can get long, very long. In fact, a mass driver that has a peak acceleration of 3 Gs, a value perfectly okay for the human body, must be about 1,700 kilometers long to achieve a takeoff velocity high enough to achieve orbit. That is far too much to build a mass driver almost anywhere on Earth, or at least one that does accelerate the vehicle all the way to orbit. So mass drivers either have to be a lot shorter and therefore accelerate less, or accelerate faster, making the G-forces harder to withstand. Both not the best things to happen. The problem with the enormous lengths has resulted in mass drivers not being used at all for the entirety of history, at least for space launches. Scaled-down variants of mass drivers are in use today as railguns or catapults on aircraft carriers. The only real concept for a mass driver that I know was actually designed by the Nazis during World War II. To satisfy Hitler's need for an aircraft that could strike the American continent, a German engineer named Eugen Sänger envisioned a suborbital spaceplane that would be propelled by rocket engines and use aerodynamic drag to increase range. The concept of Sänger's so-called Silbervogel is so insane yet genius that I may do an entire video about the concept at some point in the future. But the really interesting part about the Silbervogel is the way it lifted off. To gain enough speed for the engines to reach 140 kilometers in altitude, the spaceplane was accelerated by a rocket sledge racing along a metal track. Upon reaching about Mach 2, the Silbervogel would lift off and start its ascent under own power. But this all remained a concept since the war didn't exactly went the way the Third Reich hoped for. Now that we covered the 4 main approaches on non-rocket space launch, it's time to take a look at some way more crazy ideas. Every method we considered so far uses some kind of accelerator, either on the ground or on a plane flying at a few kilometers in altitude. But there have obviously been quite a few ideas of bringing such systems into space to reduce delta-V requirements, as well as the loss created by gravity and air resistance. The most famous one is actually very well known due to frequent use in science fiction: the space elevator. Essentially a satellite in geostationary orbit connected to the surface of Earth by a long wire, space elevators can transport cargo up into geostationary orbit without consuming any type of fuel. When using complicated counterweight systems, a space elevator can even operate without using external energy at all. The only real disadvantage of a space elevator is its position in space. Due to being permanently connected to the Earth's surface, the elevator is limited to transporting satellites and people into one specific orbit that even requires maneuvering to get payloads into position. But the biggest challenge is building a space elevator. I mean, that one should be obvious. And the second crazy idea I wanted to mention in this section is the so-called launch loop. This proposed system basically combines the advantages of a space elevator and a mass driver. Using a special accelerator, a cable loop is continuously fired toward space. To reduce air resistance, the whole thing is encased in a vacuum tube. By attaching electromagnets to the tube and utilizing a magnetic cable, the energy of the cable being fired upwards is transferred into the tubing and generates the lift needed to keep the whole structure up. To flatten the resulting parabolic shape of the loop, the vacuum tube is held down by cables. Therefore, the cable never exceeds an altitude of 80 kilometers. The flat section at the top of the loop, ideally about 2,000 kilometers in length, is also equipped with electromagnets on the outside. Spacecraft can be transported up to this track using elevators and then get accelerated by what is essentially a mass driver outside Earth's atmosphere. Upon reaching orbital velocity, the payloads are disconnected from the loop and put into their final orbit. As crazy as the idea of a launch loop sounds, it is actually possible, at least on paper. But the technologies needed to construct such a loop that seems to defy laws of physics are still on the horizon, and the pure cost of operating it make the idea almost impossible to realize. There may be even crazier methods of achieving orbit without rocket power, but many of them are just pure science fiction. After carefully looking at a total of 6 different alternative rocket designs, it may be astounding that almost none of them do exist in our world. Although physics doesn't only allow them to exist, but actually claims they're more efficient than our technology of today, alternative rocket designs are often too complex or have one fatal flaw. The reason we don't use them often tends to be technology readiness or missing competitive viability. Traditional rocket technology has come far enough to be superior to most alternative rocket designs. And even if there are some attempts to achieve access to orbit using external impulse, like air-launched rockets or spin launch, the time these technologies are going to need until they are on a similarly advanced level is likely to be measured in decades. Traditional rocket technology has a head start of over 70 years after all. Anyone trying to create a working system based on non-traditional designs would have to accept frequent setbacks and reduce competitiveness for a few years in order to be successful. And that is where alternative rocket designs seem to fail in the end. Our traditional rocket technology may be less efficient on paper, but its simplicity and availability means that other approaches are, despite being better in theory, not needed at all. Surely, there are fascinating concepts out there, but unless we manage major technology breakthroughs, they will most likely remain concepts. And that's it on alternative rocket designs, how they work and why we don't use them. Let me know in the comments which one is your favorite, and if you enjoyed the video, why don't you hit the like button and subscribe to the Rocketer. I really appreciate your support. We see ourselves in the next video, and until then, I'm out. Cheers!